Welcome back to the Deep Dive. We are absolutely thrilled to have you here with us today.
It is fantastic to be back.
Today, we are doing something a little bit different. Usually, we take a specific event, maybe a biography or a single trending article, and we tear it apart.
Right, we go really narrow and deep on one thing.
Exactly. But today, we are zooming out. We're looking at a framework. It's a system that basically claims to be a cheat sheet for genius.
Which is a bold claim, a very bold claim.
It is a huge claim. But before we get into the mechanics of how that actually works, I want to give a massive shout out to the engine behind today's deep dive.
Yeah, we have to.
This entire conversation is powered by @IdeaMechanics9 on YouTube.
That's right. And if you haven't checked out their channel yet, you really, really need to. They frame the world in a way I think our listeners will appreciate.
Or for sure. Especially if you're looking for that intellectual edge.
Exactly. Their whole philosophy is that innovation is a repeatable process. It is not just a eureka moment that you have to sit around and wait for while staring at a wall.
Right. You're not waiting for inspiration to just strike you out of the blue.
Yeah.
It's not about waiting for lightning to strike. It's about building a lightning rod so you catch it every time.
I love that analogy. That's perfect.
So please do us a huge favor if you can. Pause this for just a second. Go subscribe to @IdeaMechanics9 and definitely check the description links. They have some incredible innovation tools there.
And they pair perfectly with what we're about to discuss today. It's not just theory. They give you the tools to apply it.
Totally. And as we go through today's material, we really want to hear from you.
Yeah, please leave a comment on their channel. Let us know which of these principles you see in your daily life or where you think they could be applied.
It really helps the community grow. And honestly, we love reading them.
We do.
Okay, so let's unpack this. The topic today is TRIZ. Specifically, we are looking at the first 10 principles. Now, I have to be honest, TRIZ, it sounds a bit like a sci-fi villain.
It does, doesn't it?
Or maybe a very complex geometry test you completely forgot to study for.
It has a bit of a sharp edge to it, for sure, but it's actually a Russian acronym.
Okay.
It stands for Teoria Решения Изобретательских Задач.
I am not even going to try to repeat that.
Fair enough. It just translates to the theory of inventive problem solving.
And it was developed by a man named Genrikh Altshuler, starting way back in the 1940s.
Right. And the backstory here is just fascinating because Altshuler wasn't just sitting in a room guessing. He wasn't just thinking, how should people invent things?
He went to the data.
He went straight to the data. He was working in a patent office in the Soviet Navy, of all places.
So he had access to this just treasure trove of human ingenuity.
An absolute gold mine. He analyzed something like, I think the number is around 40,000 strong patents.
And strong is the key word there, right?
It is. We're not talking about every patent for a slightly different shaped paperclip. He filtered it down from millions of filings to just the ones that solved a major technical contradiction.
A real breakthrough.
Exactly. And as he did this, he started to notice something. The same patterns. They just kept repeating over and over again.
That is the hook for me.
See?
That's what makes this so powerful. We aren't just talking about abstract theory or some, business guru philosophy.
No.
We are talking about data-driven, observable patterns.
The core premise, and it's a huge one, is that someone, somewhere, has already solved your problem.
They just solved it in a different industry.
Precisely. The problem you are struggling with in your software startup today might have been solved by a bridge builder in 1950.
Or the issue you have with your kitchen layout might have a solution that comes from an aerospace engineer.
Yes. The contexts change completely, but the fundamental patterns of the solution, they remain identical.
So our source for today is this incredible cross-industry compendium. And it shows us how the exact same logic solves problems in software code, in fighter jets.
And in your kitchen junk drawer. It's amazing how universal they are.
So that's our mission today. We are going to walk through principles 1 through 10, from segmentation all the way to preliminary action.
And the goal here is to reveal those hidden patterns. We want to give you a new lens, a new way of seeing.
So that when you look at a problem, you don't just see a roadblock.
You see a candidate for one of these principles, you see a path forward.
All right, let's dive right into principle number 1.
Segmentation.
The art of breaking things up.
That's the perfect tagline for it.
Right. So at its core, segmentation is about dividing an object or a system into independent, manageable parts.
It's a transition. You're moving from something that's monolithic, which means it's rigid, it's one giant block.
To something that's modular,
Yeah.
flexible.
Exactly. Think of it this way. If you have a massive boulder in your yard, what can you do with it?
Not much. It's a barrier. Maybe a very uncomfortable chair.
Right. It's heavy, it's singular, and it's stubborn. You can't change its shape without a huge amount of effort, but if you break that boulder down into gravel,
Okay.
or even better, if you swap it out for a pile of Lego bricks, suddenly you have infinite flexibility.
You can build, tear down, rebuild, adapt.
That is the essence of segmentation, from a rock to Legos.
And what's just fascinating here is how this plays out in the software world.
Yeah.
I mean, our sources go really deep into this idea of the monolith versus microservices.
Oh, yeah.
This seems to be like the dominant architectural conversation in Silicon Valley for the last decade.
It is a huge, huge shift in the IT world, and it perfectly illustrates Principle 1. Historically, software was built as a monolith.
One big block of code.
Exactly. Imagine a giant single program where everything is tangled together. The user login, the shopping cart, the payment processing, the recommendation engine, it's all one giant organism.
Which I guess sounds efficient from a let's just get this thing running perspective.
Yeah.
You know, you compile one thing, you deploy one thing. It feels simpler at the start.
It is efficient. Initially, that's the trap. But as that system grows, it becomes incredibly fragile.
Why?
Because everything is connected, the technical term is tightly coupled. If the payment processing code has a bug and it crashes,
The whole site goes down.
the entire website goes down, you lose the login, you lose the product catalog, you lose everything. It all comes down in one big heap.
So it's like having a house where if the toaster shorts out, the plumbing stops working and the front door locks itself.
That's a perfect analogy. It lacks what we call fault isolation.
Okay.
So applying the principle of segmentation, we get to microservices.
The Lego bricks.
The Lego bricks. In an e-commerce platform using microservices, the shopping cart is its own little island of code. User authentication is another island. Payment processing is a third.
And they talk to each other.
They talk to each other through something called APIs, which are just digital bridges. But they are independent entities. They run separately.
So let's play it out. If the payment system crashes now,
The user can still browse the catalog. They can still add things to their cart. The payment module might just throw an error message saying try again in a few minutes, but the whole ship doesn't sync just because one compartment flooded.
so that's the fault isolation you mentioned. But the notes also say it impacts how the teams work, right?
Okay.
It's not just about the code. It's about the people writing the code.
A huge impact, a massive impact. This gets into something called Conway's Law, which basically says your software architecture will mirror your company's communication structure.
Okay, so a monolithic piece of software means you have one giant team that's always stepping on each other's toes.
Pretty much.
Yeah.
You have to have endless meetings to coordinate any change. But with segmentation, with microservices, you can have a small, autonomous team that owns the cart module. They can work on it, update it, and deploy it without ever having to talk to the team working on the login module.
So it allows for speed.
Speed and autonomy. In a monolith, every time you want to update the code, you have to redeploy the entire beast, which is slow and incredibly risky.
Right.
With microservices, you just swap out the one little brick that needs changing. It's faster and so much safer.
This connects to another concept in the notes, something called object-oriented design, or O. And there's a rule mentioned here called the single responsibility principle.
A classic foundational rule of good software design. It states that a class, which is just a chunk of code, should have only one reason to change.
So what does that mean in practice?
It means if you have a piece of code that does two things, you've probably made a mistake. Let's say you have a class that handles checking a user's password, and it also saves their data to the database.
Seems efficient.
But you've violated segmentation. You've glued two distinct jobs together.
So if you want to change how the database works, say you move from one type of database to another.
You might accidentally break the password checker. You pull on one thread, and the whole sweater just unravels.
Got it.
So you segment them. You apply Principle 1. You create a user authenticator object and a separate user data store object. Two separate things, two separate responsibilities. It's safer, cleaner, and way easier to fix when something breaks.
Okay, now let's pivot hard. We are leaving the server room,
Good.
and we are jumping into the cockpit of a fighter jet. The F-14 Tomcat, this is classic Top Gun stuff.
An absolutely iconic aircraft, and a perfect physical example of segmentation applied to aerodynamics.
So the problem with airplanes, and I have to admit, I never really thought about this until I read these notes, is that the wings are always a compromise.
Always.
Yeah.
It's a fundamental contradiction baked into the physics of flight.
What's the contradiction?
Well, if you want to take off or land, you're moving relatively slowly.
Right.
To do that safely, you need wings that are straight and wide to generate a lot of lift at those low speeds.
Like a glider or a small Cessna. They have those big straight wings.
Exactly. They're designed to just grab the air and float on it. But if you want to go supersonic, those big straight wings are terrible. They're like air brakes.
They create too much drag.
Massive drag and destructive shock waves. For high speeds, you want wings that are swept back almost like an arrowhead to slice through the air efficiently.
So traditionally, a designer has to pick one shape and then just suffer the consequences in the other scenario.
That's the trade-off. A Cessna has straight wings. It can't go fast. The Concorde had those sharply swept delta wings. It was incredibly fast, but it had to land at a very high, very dangerous speed because it didn't generate much lift when it was slow.
Stable at low speed versus fast at high speed. You have to choose.
Unless you apply Principle 1, the F-14 solved this by segmenting the wing.
So the wing isn't just one fixed piece of metal fused to the body of the plane.
No, it's a separate part that sits on a massive, powerful pivot. It's a variable sweep wing.
It physically transforms in midair.
It does. It's incredible to watch. On takeoff, the wings swing all the way out, perpendicular to the fuselage maximum lift. It behaves like a slow, stable plane.
And then when they want to go fast.
Once it hits altitude and the pilot hits the afterburners, the wings sweep back, tucking in tight against the body. Now it has minimum drag. It's an aerodynamic arrow.
So by segmenting the wing from the body and allowing it to move, you get the best of both worlds.
You resolve the contradiction.
Yeah.
You get a plane that is good at being slow and good at being fast.
Quick question, though. If it's such a perfect solution, why don't all planes do this?
Because TRIZ solves one problem, but engineering often introduces another one. That pivot mechanism, the gearbox, to move those wings against incredible aerodynamic forces.
Yeah.
It's extremely heavy, complex, and a nightmare to maintain.
So you trade aerodynamic perfection for mechanical complexity.
Exactly. So for modern stealth fighters, they've found other ways to solve this with computer controls and different wing shapes. But as a pure illustration of Principle 1, the F-14 is a masterclass.
And the notes give another aviation example, which seems obvious now, but is still segmentation. The landing gear.
Same exact logic. You need wheels to take off and land. That's non-negotiable.
Right.
But flying around with your wheels hanging down in the wind is like dragging a parachute behind you. It ruins your fuel efficiency and your speed. It's pure drag.
So we segment the gear.
We make it a separate, movable system. We make it retractable. It separates from the airstream by tucking inside the plane.
So it's there when you need it, and it's gone when you don't.
Another perfect example of segmentation. The plane and the wheels are not a single fused unit.
Let's look at something we see on the highway every single day, the semi-truck.
This is segmentation applied to the world of logistics, and it's so common we don't even think about it.
Right. But imagine if every delivery truck was a single unit. The engine and the storage box were all welded together. A monolith.
It would be a nightmare. If you needed to ship milk, you'd need a purpose-built refrigerated truck. Then, the next day, if you needed to ship lumber, that expensive refrigerated truck is completely useless. You'd have to go buy a whole separate flatbed truck.
Incredibly wasteful. And wildly expensive.
So the automotive industry segmented the power from the cargo. The tractor, which is the engine and the driver's cab, is independent of the trailer, the cargo box.
So you can swap them out.
In minutes, you can swap a refrigerated trailer for a flatbed or a tanker. The expensive part, the engine, the tractor, it never stops working. It just drops one load and picks up the next. Meanwhile, the cheap part, the container, changes based on the job.
That's modularity at a massive scale.
Yeah.
And bringing it right back into our pockets, foldable smartphones.
This is a very modern battle against a classic contradiction.
The contradiction being, I want a huge screen to watch movies and browse the web.
But I wanted a small device that fits comfortably in my pants pocket.
You can't have both. A big screen is, by definition, not small.
Unless you segment the screen. By using flexible materials or a very clever hinge, companies like Samsung allow the device to physically fold in half.
So it's segmentation, allowing a device to be large and small at the same time.
It resolves the contradiction. It's Principle 1, right there in your hand.
I love that. Okay, moving on to principle number 2. This is taking out, or Sometimes it's called extraction.
This is one of my favorites because it's about minimalism.
Yeah.
It's like the Marie Kondo of engineering principles. Does this part spark joy? No. Take it out.
So the definition here is removing a disturbing part or property from an object.
Mm-hmm.
Or conversely, singling out the only necessary part and getting rid of the rest.
Think of it as trimming the fat, or sometimes it's more like performing surgery to remove a tumor. You have a system, it mostly works, but there's this one thing about it that makes it annoying or harmful or inefficient.
And the classic example provided is wireless earbuds.
A perfect example. For 50 years, what was the single most disturbing part of using headphones?
The wire. No question. It tangles in your pocket, it catches on doorknobs, it frays and breaks, it tethers you to your device.
But you needed the wire, right? That was the only way to get the electrical signal for the sound from your Walkman to your ears. The wire was the carrier.
So TIZ says,
the wire is disturbing. Take it out. By developing technologies like Bluetooth, we extracted the physical connection. We kept the essential function, the sound, but we removed the disturbing component.
Another great household example is the vacuum cleaner, specifically the Dyson Revolution.
Right. James Dyson looked at the standard vacuum cleaner of the day and he asked, what is the weak link? What is the most disturbing part here? And it was the bag.
The bag was a problem.
It was a huge problem. First, it was a consumable. You had to keep buying them, which is annoying. But worse, from an engineering perspective, was what happened as it filled up with dust.
It loses suction.
It loses suction because the tiny pores in the paper bag get clogged. The bag was actually killing the primary function of the machine.
It's a paradox. The thing that's supposed to collect the dust is preventing the collection of dust.
A classic technical contradiction. So he applied principle 2, taking out. He took the bag out of the equation entirely.
And replaced it with the clear bin and the cyclone technology.
Right. He kept the dust collection function, but removed the component that caused the systemic failure.
Let's look at an industrial application, fiber optics. This one is really interesting to me because it's about separating properties, not just physical parts.
This is a bit more abstract, but it's an incredibly powerful way to think. Imagine you need bright light to illuminate a priceless, delicate painting in a museum.
Okay.
Or maybe you need to see inside a human body during laparoscopic surgery.
You need a lot of light in both cases.
A lot of light. But the problem is traditional light sources, incandescent bulbs, halogen bulbs, they generate a ton of heat along with the light.
And you can't put a hot bulb right next to a Van Gogh painting or inside a patient's abdomen.
No, you'd cause irreparable damage. Heat is the disturbing property. So how do you get the light without the heat?
You take the heat out.
You use fiber optics to take the heat out. You put the hot light bulb in a box safely across the room. You keep the bad property over there. Then you use the fiber optic cable to extract only the light and transport it to the target.
You've effectively filtered the output.
You've taken out the heat from the point of illumination. It's a brilliant application of the principle.
That reminds me of the other example in the notes, the noisy compressor in an air conditioning system.
It's the exact same principle. A standard AC unit has 2 outputs. Cold air, which is good, and a ton of noise and vibration, which is bad.
Right. So with an old window unit, you get both.
You get the cold air, but you can't sleep because it sounds like there's a lawnmower in your bedroom. So modern split system ACs segment the system and apply taking out.
They move the loud part outside.
They extract the noisy part, the compressor and the fan, and shove it in a unit outside the building. All you have inside is the quiet evaporator that delivers the cold air. They separated the good from the bad by putting distance between them.
And finally, under this principle, we have a software business model. SaaS, software as a service.
Right, also known as the ASP model, or application service provider.
So in the old days, say the 90s or early 2000s, if your company wanted to run big business software like a CRM or an accounting package,
you had a lot of work to do. You had to buy physical servers, build a server room, hire an IT team to install the software, manage the databases, handle backups, and deal with all the updates and patches.
all of that was disturbing work.
It was a massive headache. It wasn't your core business. It was just expensive overhead.
So SaaS companies like Salesforce or Google just took out that complexity.
Exactly. They said, forget all that. We will host it. We will update it. We will secure it. We'll handle the backups. They extracted the entire hosting burden from the customer.
All you have to do is log in through your web browser.
They took out the friction.
Yeah.
It's principle 2 applied to a business model.
It's amazing how these principles apply just as well to business models as they do to jet engines. Okay, let's move on to principle 3, local quality.
Or, as the tagline says, one size does not fit all.
That's it. So local quality is about moving from a uniform structure to a non-uniform one. It's about optimizing specific parts of an object for the specific job they do, right there in that local spot.
You know, a lot of lazy or cheap design creates uniform objects just because it's easier to manufacture. A steel bar is the same grade of steel all the way through. A plastic bucket is the same plastic everywhere.
Right.
But nature almost never does that. A tree isn't the same material in the bark as it is in the heartwood. Your own bone is different at the joint surface than it is in the main shaft.
So smart engineering should do the same. It shouldn't use uniformity if the demands on the object are different in different places.
Precisely.
And the example that everyone has held in their hand is the pencil.
The humble pencil is a beautiful, beautiful example of local quality. Just look at it. One end is made of graphite mixed with clay. Why? Its local function is to leave a mark on paper.
The other end is rubber.
Right. Its local function is to remove a mark. And the middle is wood. Why? Its job is to be rigid, cheap, and easy to hold.
If the whole pencil were uniform, if it were all graphite, it would be a brittle, messy stick.
And if it were all rubber, it wouldn't write. If it were all wood, it would be useless for both. The material changes based on the local function required at that specific millimeter of the object.
Lunchboxes are another great everyday example.
A simple bucket is uniform. You just throw everything in, and your soup leaks on your sandwich.
It's a terrible design.
Awful. But a good lunchbox has local quality. It has an insulated compartment to keep the thermos of soup hot. It has a sealed compartment for the applesauce so it doesn't leak. It has a rigid compartment for the sandwich so it doesn't get squashed.
Each zone is locally optimized for its specific cargo.
It's not a monolith. It's a system of specialized zones.
And multi-blade razors. I admit I always thought that was just a marketing gimmick now with 5 blades. But there is actually some local quality engineering going on there.
It's surprisingly technical. The blades aren't just 5 identical knives stacked on top of each other.
They do different jobs.
They often have different local functions. The very first blade might be angled slightly to act as a lifter. It's designed to gently pull the hair up and out from the follicle. The second blade then does the primary cutting.
In the ones after that.
The trailing blades might be angled differently to cut even closer, or to act as a squeegee to clear away the shaving foam. They work in concert, each with a specialized role.
Now, in manufacturing science, this gets really cool. The notes talk about metal quenching.
This is absolutely crucial for high-performance metal parts, like gears in a transmission, or ball bearings, or even ancient samurai swords.
And there's a contradiction here, right?
A big one. For a gear tooth, you want the surface to be incredibly hard so it doesn't wear down from friction. But super hard metal is also super brittle. If you hit it with a hammer, it shatters like glass.
So you can't have the whole gear be that hard, or it would break under shock loads.
Right. You want the inside, the core of the gear, to be softer and tougher, more ductile, so it can absorb impacts and shocks without cracking.
So you need to be hard and soft at the same time.
And you achieve that with local quality. You use processes like case hardening or carburizing. You treat the metal so that the chemical composition of the surface is different. It's infused with carbon to make it hard and wear resistant, but the core remains its original, softer, tougher steel.
So the quality of the metal physically changes as you go deeper into the object.
Yes, it's non-uniform by design.
And chemical engineering uses this with temperature gradients in distillation columns.
Right. If you look at those huge towers at an oil refinery, they aren't one uniform temperature inside. They are very hot at the bottom and get progressively cooler as you go up.
And that gradient is the tool.
That gradient is the machine. It allows different chemicals in the crude oil, which have different boiling points, to vaporize and then condense at different heights in the tower. That's how you separate gasoline from kerosene from asphalt. The non-uniformity is the entire point. If the tower were the same temperature throughout, it would be useless.
And just to touch on the business application, quickly, market segmentation.
We use the word segmentation there, but in the context of TRIZ, it's really applying the principle of local quality to people.
You don't treat the entire market as a monolith.
No. You don't send the same advertisement to an 18-year-old college student that you send to a 65-year-old retiree. You tailor your quality, your message, your product features, your price point locally to the specific demographic you are targeting.
Okay, let's move on to principle 4, asymmetry. The tagline is breaking the mirror.
I like that one. Humans have this deep, innate love for symmetry. We find it beautiful. We see it in faces, in butterflies, in classical architecture. But from an engineering standpoint, symmetry is often inefficient.
So the definition here is changing the shape of an object from symmetrical to asymmetrical, specifically to improve its function.
Let's look at industrial mixing. If you have a perfectly round symmetrical mixing vessel, like a big steel bowl, and you put a perfectly symmetrical paddle in the middle to spin, what happens?
It mixes.
Not really. You often get what's called a dead zone. The liquid just spins around in a perfect circle with the paddle. It's called laminar flow. It's more like a liquid carousel than a mixer.
Ah, so it's not actually folding over on itself.
Exactly. But now, if you add some asymmetry, if you add a few fixed baffles to the side of the bowl, or if you make the paddle itself asymmetrical, maybe a bit crooked,
You introduce chaos.
you introduce turbulence. The liquid hits the baffle, bounces back, and folds over itself. That's what mixing is. Asymmetry creates the function. It's why cement trucks have those weird spiral-shaped veins inside. They're designed to be asymmetrical to tumble the concrete.
And this applies to ergonomics, too.
Absolutely. Look at your hand. It is not a symmetrical cylinder. Your palm has a curve. Your thumb is off to one side. So why should the handle of a power drill or a screwdriver be a perfect symmetrical cylinder?
It shouldn't.
No. Ergonomic tools are often weirdly shaped. They're lumpy and asymmetrical because they are designed to fit the asymmetry of the human body. That reduces fatigue and increases control.
There's a very simple, very clever mechanical example in the notes, too. The flat spot on a shaft.
Anyone who's ever tried to build something knows this pain. You have a round metal rod, a shaft, and you need to attach a knob to it with a little set screw.
Right.
If the rod is perfectly round and smooth, perfectly symmetrical, the screw just presses on a single point, it slips, the knob just spins around the shaft.
So what do?
You take a file and you grind down one side of the shaft, you create a little flat spot, you introduce asymmetry.
And now the screw has a flat surface to push against.
And it locks. It physically cannot rotate. That tiny, simple act of breaking symmetry is what makes the connection secure.
Okay, let's combine the next two principles, because they are described in the source as being cousins.
They are very closely related.
We have Principle 5, merging, which is about consolidation, and Principle 6, universality, which is about one thing doing many jobs.
You can see the overlap. Merging is about bringing different objects together in space or time. Universality is about making one object perform the functions of several others.
So under Principle 5, merging, the smartphone is, again, the ultimate champion.
It really is. It is the poster child for merging. It physically consolidated the telephone, the camera, the GPS navigator, the voice recorder, the flashlight, the music player, and for many people, the laptop.
All into one single glass and metal brick.
It's an incredible act of consolidation.
There's a cool aerospace example here about merging the skin of an airplane with its sensors.
This is really cutting-edge stuff, or what they call smart structures. Usually, if you want to know the stress on a wing, you build the wing, and then you stick a sensor on the wing.
Two separate things.
Two things. But by using the principle of merging, engineers are now embedding hair-thin fiber optic strain gauges directly into the composite material as they build the wing.
So the skin of the wing is the pressure sensor.
Exactly. You have merged the structure and the sensor into one single intelligent object. There's no longer a distinction between the two.
Okay, now let's look at its cousin, Principle 6, universality, the Swiss Army knife principle.
Literally. That is the icon of universality. You have one handle, one object, but it performs the function of a knife, a screwdriver, a can opener, a pair of scissors, a toothpick. The object has universal utility.
It's one thing that can do many different things.
Whereas the smartphone merged many things into one. It's a subtle but important difference. The camera in your phone is still a camera. The Swiss Army knife's main blade is also the handle for the screwdriver.
I see, okay. So in aerospace, there's the example of the pitot-static probe.
Right. We mentioned these parts before. Traditionally, you have a pitot tube, which is a forward-facing tube that measures ram air pressure to determine your speed. And then somewhere else on the fuselage, you have a static port, which is a flush-mounted hole that measures ambient air pressure to determine your altitude.
Two systems, two holes in the plane, two sets of plumbing, two things to maintain and de-ice.
Right. But by applying universality, you can design a single multi-function probe that has openings to capture both dynamic and static pressure in one unit. One component, one hole in the aircraft, performing two distinct jobs. That's universality.
And that saves weight, it saves space, and it reduces drag.
And in the world of aerospace, weight is everything. Every single ounce you save is extra fuel, or extra payload, or better performance. Universality is a key tool for that kind of optimization.
Which leads us perfectly into Principle 7, nested doll, or nesting.
The Matryoshka doll principle. One thing fits inside another.
So the core concept is placing one object inside another, usually to save space or to provide some kind of protection.
We see this all the time. Telescoping antennas, zoom lenses on cameras, stackable measuring cups. But the aerospace example provided in our source is a really, really clever solvec, a specific solution to a very specific problem.
And this is the ventral UHF antenna.
Right. So modern airplanes have these little holes on the fuselage called static ports that measure air pressure. We just mentioned them. They are absolutely crucial for telling the pilot their altitude and airspeed.
And if they get clogged?
If they get clogged with bugs or ice or even a piece of tape while the plane is parked on the ground, the pilot gets dangerously wrong data that can be and has been fatal.
So you have to cover them when the plane is on the ground?
You do. But you can't rely on a manual cover, one of those red tags that says remove before flight, because people are human, they make mistakes. A ground crew member might forget to take it off.
So you need an automatic solution.
And this is where the engineers used nesting. There is a UHF communications antenna on the belly of the plane. It's a small blade. The engineers designed it so that when the landing gear is down, which only happens when the plane is on the ground.
The antenna tucks inside, it nests into the landing gear bay.
Exactly. And its stowed position is designed to physically block and cover the static port. The antenna itself becomes the protective cover.
That's brilliant.
And then when the plane takes off and the pilot retracts the gear doors close, and the antenna swings out from its nested position to do its primary job as a radio antenna.
So it nests to perform a secondary function protection, and then it deploys to perform its primary function.
It is such a graceful, elegant use of geometry and system states. It's using the downtime of one component to provide a service to another.
It's the idea that nothing in a system should ever be truly idle.
That's an advanced engineering concept right there. If a part isn't doing its main job, can it be doing a secondary job? Nesting is often the principle that unlocks that possibility.
Okay, Principle 8, anti-weight.
Also known as counterweight.
And let's be clear, this is not about anti-gravity drives from science fiction.
Unfortunately, no, not yet. It's about using a counterforce, often gravity itself, to balance an object or make it feel lighter.
The elevator is the example we all trust our lives to every day.
It is. And most people have a completely wrong mental model of how an elevator works.
They think the motor at the top of the shaft is just hoisting the car up on a cable, like a fishing reel.
If it did that, the motor would have to be the size of a small car. Think about the energy required to lift a heavy steel box with 10 people in it, hundreds of feet in the air.
So that's not what's happening.
No. The motor is not lifting the car. There is a massive stack of metal plates, the counterweight, that is hanging on the other side of the main pulley.
And the counterweight is really heavy.
The counterweight is typically engineered to equal the weight of the empty elevator car, plus about 40 to 50% of its maximum passenger load.
So the motor's just lifting the difference.
It's just lifting the difference. If the car and the counterweight are perfectly balanced, the motor effectively has to lift 0 pounds. It just has to overcome friction to get things moving. It's an enormous energy saving.
You use weight to fight weight.
That is anti-weight. You're using the force of gravity on the counterweight to negate the force of gravity on the car.
There's a great industrial example in the notes involving floating logs.
Right. Wood usually floats, but some very heavy, dense hardwoods might sink, or they might sit so low in the water that they're difficult to tow efficiently in a river.
So they use a foaming agent.
They do. It's like a specialized form of styrofoam.
Yeah.
They attach a block of this buoyant foam to the heavy logs. The foam provides an upward force buoyancy that acts as anti-weight.
It cancels out some of the log's density.
It does. It makes the entire assembly float high in the water for easy transport. You're creating artificial buoyancy. You're using one force to neutralize another.
Okay, we're coming into the home stretch here. Principle 9, preliminary anti-action.
The preemptive strike.
I like that. The definition is anticipating a harmful event and acting beforehand to neutralize it.
The key word there is beforehand. This is not about reacting to a problem. This is about knowing something bad is going to happen, and you punch it in the face before it can even stand up.
Construction gives us the incredible example of pre-stressed concrete.
This is fascinating structural physics. Concrete as a material is amazing at being squeezed. It has incredible compressive strength. You can pile a skyscraper on it and it won't crush.
But it's terrible at being pulled.
Terrible. It has almost zero tensile strength. If you pull on it or try to bend it, it cracks almost immediately.
And beams, like in a bridge or a parking garage, they bend under a load.
They do. When you drive a heavy truck onto a concrete beam, the top surface of the beam gets compressed, but the bottom surface gets stretched. That's tension. And concrete hates that.
So how do you fix it?
You use preliminary anti-action. Inside the mold for the beam, they place high-tensile steel cables or rebar. And before they pour the concrete, they use hydraulic jacks to stretch that steel tight like a giant, powerful rubber band.
So the steel is under incredible tension.
Right. Then they pour the wet concrete into the mold around the stretched steel. They let it dry and harden. Then they cut the ends of the steel cables.
Snap.
Snap. The steel tries to shrink back to its original shorter length. And in doing so, it squeezes the concrete from the inside. It puts the entire beam under massive compression.
So it's pre-squeezed.
It's pre-compressed. So now, when you put that heavy truck on the bridge and the beam tries to bend, the tension on the bottom first has to overcome all of that built-in compression before the concrete even feels any tension at all.
You've preloaded the solution into the material itself.
You've neutralized the harm of tension before the load even touches the bridge. It's an absolutely brilliant invention.
A much simpler but equally vital example is the lead apron at the dentist's office.
Simple, but perfect. The X-ray, the harmful event is coming. You don't put the apron on after the exposure. That would be useless. You perform a preliminary anti-action shielding before the event occurs.
And in chemistry, there are buffer solutions.
Same exact logic. If you're running a chemical reaction and you know it's going to produce a lot of acid, which could ruin the reaction, you don't wait for the pH to crash. You add a chemical buffer to the mix at the very beginning.
The buffer lies in wait.
It just sits there.
Yeah.
As soon as the first molecule of acid appears, the buffer chemistry neutralizes it. It preemptively stops the pH spike from ever happening.
And that brings us to the last one for today, Principle 10, preliminary action.
Now, this sounds very similar to the last one, but there's a key difference.
Right. Principle 9, preliminary anti-action, was about stopping a bad thing from happening.
Principle 10, preliminary action, is about helping a good thing happen faster or more safely or more easily.
It's prep work.
It is pure prep work. It's the concept of mise en place in a professional kitchen. You chop all your onions and prepare all your ingredients before you even think about turning on the stove.
The source gives the everyday example of pre-pasted wallpaper.
A classic DIY convenience. The factory knows that the end user, you, will need to apply paste to the wallpaper. Applying paste is messy, it's slow, it's inconsistent, so they perform a preliminary action.
They put the paste on at the factory.
They apply a layer of dry adhesive at the factory. They did that messy step for you in advance. All you have to do is add water to activate it.
Surgical trays are another critical example.
Absolutely. When a patient is bleeding out on the operating table, you do not want the nurse to be fumbling around looking for a scalpel and then having to sterilize it.
No, that would be chaos.
So hours or even days before the surgery, a team performs the preliminary action of gathering all the required instruments, sterilizing them, organizing them in a specific layout on a tray, and then sealing it.
So it's ready to go instantly?
That prep work saves critical life-saving time during the main process.
And in the world of manufacturing, there's Kanban, or just-in-time inventory systems.
Kanban is all about preliminary action signals. You don't wait until the worker on the assembly line runs completely out of bolts to order more.
That would cause a shutdown.
Right. The system is set up so that when the worker takes the last bin of bolts, that empty bin itself becomes a signal that goes back to the warehouse to prep and deliver the next batch. The movement of goods is prepared in advance of the actual shortage.
There's a really cool aviation safety example here, too, the air pulse.
This is a proactive safety measure. We've talked about how pitot tubes can freeze or get clogged. Instead of waiting for the sensor to fail and the pilots to lose their airspeed information,
Which is a catastrophic failure.
some advanced systems use a preliminary action where they periodically automatically blast a short burst of high-pressure air through the lines.
Just to be safe.
Yeah.
Like a little cough.
Exactly. Just to purge them of any moisture or insects that might be starting to build up. They don't wait for a clog. They perform a preliminary cleaning action to ensure the main function of sensing is never interrupted.
And the final example is about tape removal.
This is so clever. Sometimes sensitive sensors or engine inlets are taped over for protection on the ground. Forgetting to remove that tape is a classic and dangerous human error.
So how do you use preliminary action to fix that?
The designers create the tape with a specific tab or flap that is designed to catch the wind. They've done the prep work in the design of the tape itself.
So as the plane speeds up for takeoff.
The wind, the ram air, automatically grabs that tab and rips the tape off safely. The action of removal is prearranged to happen automatically by the environment itself.
So that is it. 10 principles. From chopping things up with segmentation to doing the prep work with preliminary action.
It's a lot to take in, but if you just remember that core mission, that innovation is a repeatable process.
It really does change how you look at the world. You stop getting frustrated at bad design, and you start kind of diagnosing it.
Yes, you look at a poorly designed product and think, oh, that's a clear failure of principle 2. They should have taken out that annoying part.
Or, why is this handle so uncomfortable? It desperately needs some asymmetry.
You start seeing the principles everywhere.
So here is our final challenge to you, the learner. Look around the room you are in right now. Find the most annoying, the most frustrating object that's near you.
It could be a confusing remote control, a wobbly chair, a coffee maker that spills everywhere.
And ask yourself, which of these first 10 principles did the designer completely ignore? And more importantly, how could you apply one of them to fix it?
Could you segment it? Could you use anti-weight to make it easier to lift? Could taking out remove the part that always breaks?
It's a fun little game, but it's also exactly how you train your brain to start thinking like an inventor.
Absolutely. It's about building that mental muscle.
We want to remind you one last time. This deep dive was powered by our friends at IDM Mechanics 9 on YouTube. Please go subscribe to their channel. It's the place to go if you want to turn these kinds of insights into actual applicable skills.
And really check the description for those innovation tools they've put together. They're absolutely worth your time.
And please leave a comment on their videos. Tell us about that annoying object in your room and how you'd fix it with TRIZ. We genuinely love reading those.
It was a real pleasure walking through this with you all today.
Until next time, keep diving deep.